So the chain rule, so in this section we're going to discuss the chain rule for functions of multiple variables, and we will look at what you call implicit differentiation. Remember implicit differentiation from Calc 1? A little bit of a nightmare, right? Long problem. Well, actually, if you think implicit differentiation is going to be harder in Calc 2, in Calc 3 rather, I have good news for you. It's going to be an easier process. Actually, you would wish you knew this back when you were in Calc 1. So, okay, let's go. Let's discuss the chain rule first. So here's the thing. If we have a function z that depends on two variables, but at the same time those two variables have an intermediate have another variable, well, then the chain rule would be, so the derivative of z. Notice this is an ordinary derivative. This is not a partial derivative. So that will be given by the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. And of course, we can extend this to as many variables as you want. Okay, let me give you a picture. So we can see why some of the factors there have the Jacobi's d, while some of the other factors have the regular d. So remember those diagrams we did to follow the orders of the differentiation? Well, so for the first example, where we have a function that depends on x and y, and at the same time x and y both depend on t. Well, so this is the diagram. The diagram will help us a lot. So z is primarily changing, depending into variables, that is x and y. And at the same time, both x and y depend on one single variable, t. All right? So the reason we have partial derivative symbol to go from x to x, to go from z to x and y, that's because z has two different options. Go to x and go to z, and in this case we need to describe partially those two changes. And in this case, dx dt, dy dt are not partial derivatives, because to go from x to t and y to t, there's only one single variable, so no partial differentiation is needed. So let's have a look at this first example using the chain rule, and then substituting and then differentiating, because we're going to solve this into different ways. Okay, so using the chain rule, that is dz dt equals to the partial of z with respect x times dx dt plus the partial of z with respect to y times dy dt. So that is, we're describing the contributions of the change in the x going along the x branch and the contributions to the change of the function in the y branch. So that's why I started with this example, having one variable and then all the other two variables, x, y, and z. All right? But well, this is something simpler. Grab the idea first, okay? So let's color code this so you can see how we're going to go. So we're going to go from z to x, and then from x to t. That's going to describe this first term. All right, so first of all, what is the partial derivative of the function z with respect to x? So number one, the derivative of x, y squared, is 1 times y squared, plus the derivative of 3x squared, that's a 6x, minus 4y, well, that's 0. Okay, let me put parentheses around, because I'm going to multiply by the derivative of x with respect to t. So now let's have a look at the expression x, which depends on t. Well, what's the derivative of e to the t? Isn't that just itself, e to the t? E to the t. So that is dz dt. Don't freak out if you're seeing a lot of variables, x's, y's, t's. We'll simplify this in a second. So that is plus. So dz dy, that is, now I'm going to go the other way. Let me use a different color to highlight this. So this time we're going to go z with respect to y and y with respect to t. That's what's going to describe the second term. All right. So that is the partial derivative of z with respect to y. Here with respect to y, that's 2xy plus 3x squared with respect to y, that's just a constant, that's 0, minus 4y, that's minus 4. And then we need to multiply by the derivative of the y equation that depends on t, that is negative sine t. Okay, so we're done with the calculus here. We're done with finding the derivatives. Well, here is a problem. Not a problem, not necessarily a problem. So here we are differentiating a function z with respect to t. We need to get rid of these x's and y's and turn them in terms of z's. In terms of t's rather. So we're going to use these substitutions here. Okay. So x equals to t, wherever we see the letter x, replace with e to the t, and y equals to cosine t, replace every instance of y with cosine of t. All right. So that equals dz dt equals to cosine squared t plus 6 times x, which is e to the t, times e to the t, plus 2 times the quantity x, which is e to the t, times y, which is cosine t, everything multiplied by negative sine t. All right? You see how our final result is an expression that depends only on one single variable, t? No more x's and y's? Yes.
What happened to the minus 4?
The minus 4, oh, yeah. Minus 4, thank you. Right? Minus 4. So let's simplify this a little bit. I think it's worth doing it. Why not? So that is e to the t cosine squared t plus 6 e to the t times itself, it's e to the 2t. And then 2 times negative sine, careful, that's minus 2 e to the t sine cosine, sine t, cosine t, and then minus 4 minus minus equals plus 4 sine t. So that is our derivative, right? Using the chain rule. All right. So that is letter A, using the chain rule. That is following the diagram, which is important to see because that way it gives us an idea of how is the function changing with respect all the variables, well, depending on how they are given or how they are represented. So this time, for part B, it's by writing z as a function of t and then differentiating. Well, so here we have z equals to, I'm going to replace every instance of x with e to the t, that is e to the t, and then y squared, that is cosine squared t, plus 3x squared, that is 3 e to the 2t, yes, because e to the t squared, it's e to the 2t, not e to the t squared, careful, and then minus 4 quantity y, which is cosine t. So do you see how this time we're starting with a single variable function? No more chain rule. This is just a calculus 1 problem this time, right? So, okay, let's find the ZDT. For real? There we go. So let's find the derivative, and we should get the same result as in part A. That is dz dt equals, oh, here, careful, we're going to need a product rule along with a mini chain rule. So using the product rule, the derivative of e to the t is itself e to the t times cosine squared t plus the derivative of cosine squared, which it's going to be negative 2 cosine t times the derivative of of cosine, which is negative sign, but I already had the negative, that's sine t. So that is the derivative of the product, right? Oh, times the e to the t. Don't forget the e to the t, the u part, right? Again, this is u prime v plus v prime u, okay? Let's differentiate the second term, 3e to the 2t, that's plus 6e to the 2t. And lastly, plus, because the derivative of cosine is negative sine times the negative is positive, 4 sine t. Okay? So, do you see how we have the same result? E to the t cosine squared t. Let me just clean up this. Let me clean this up. That is plus 2 e to the t, or rather minus, cosine t sine t, plus 6 e to the 2t plus 4 sine t. Same result as part B, right? Two different ways. The chain rule way, and then by first expressing as a function of a single variable function, which in this case is t. All right? All right. In the next page, what do we have? So it looks like we have a word problem in the next page. Again, it's a chemistry problem. It's very similar to that problem we did in the almost at the end of the previous lecture. So what do we have? So and you can think of this as a related rates type of problem, but with multiple variables. Okay. So what we have, the pressure, volume, and temperature of a mole of gas, of an ideal gas, are related by the equation PV equals 8.31 T, where P is measured in kilopascals, volume in liters, T in Kelvin. Find the rate at which the pressure is changing when we're experiencing two changes. That is, the temperature is increasing, right, at a rate of 1 Kelvin per second. Notice we have units of time, right? That's because we're introducing this new variable T for the functions. And what else? The pressure is changing with a temperature. The volume is 100 liters, and it's also increasing at a rate of 0.2 liters per second. All right? So in this case, unlike the previous situation we had last time, so we were defining, say, a pressure that depended on volume and temperature to control volume and temperature to see what was the effect on the pressure, or solve for the volume to control pressure and temperature, or solve the temperature for temperature to control pressure and volume. No, in this case, all three variables are changing with respect to time. All right. Remember that that classical problem in Calc 1 when you were first taught about that related rate. You had the snowball getting bigger or melting, right, at different values of time. Well, here we have the same situation, but with three variables changing at the same time. All right. Before setting an expression and before doing any calculations, let's see what we have and what are they asking us to compute. Okay, so number one, so they're asking us to find, where is it? The rate at which the pressure is changing when the temperature, the change of the pressure with respect to time, all right? So that is our unknown in this case. So they're telling us that the temperature equals 300. And the change of the temperature with respect to time, that is 0.1. Also, they're telling us that the volume equals 100, and the change of the volume with respect to time, that is 0.2. Before writing an equation, before writing anything, well, let's see how is this function working, okay? So, number one, because we want to know the change in the pressure, let's solve for the pressure first. So that is P equals to 8.31 T, divide both sides by V, that makes it a V to the negative 1. All right? But the thing here is, we have a situation where the pressure is controlled by the temperature and the volume. All right. However, that's not the only. Those are just the intermediate variables, temperature and volume, because we're not just measuring. We're not just controlling temperature and volume. We're controlling them in terms of time. So these two, furthermore, vary with respect to time. That means we're going to set up a chain rule expression for the part of the pressure that is contributed from the temperature branch plus the part of the change that is contributed from the volume branch. All right, let's write our expression first. So that is dp dt. Notice in this case, okay, actually I'm going to make a mistake on purpose to see if you can catch this. Okay, so dp dt, temperature first, times dt over dt, plus the change in the contribution for the volume, dp dv, times dv dt. Where's my mistake? Yes.
You didn't use partial differentiation for dp dt and dp dv.
Right? Why should I use partial derivatives again?
Because pressure is like expressed with multiple variables.
Exactly. P is depending on two variables, not just one variable. So let me change this to Jacobi's d's. So why aren't these Jacobi's d's?
Temperature and volume were both expressed with over time.
And yes, they're expressed over time, right? But still, why are these just ordinary derivatives and not partial derivatives? Because it's a single variable, right? Because temperature and volume only depend on a single variable. Yes, you see two T's, yes, but that's for each independent branch, the temperature and the volume. That's correct. All right, well, let's put numbers, symbols, and everything we need to get this result. Okay, so number one, let's find the partial of the pressure with respect T. So number one, the partial of the pressure with respect T, we're going to get those partials from the equation we had defined at the top. So with respect T, that's just 1 times 8.31 v to the negative 1. But I need to multiply by the rate of change of the temperature with respect time, which is a given, isn't it? Isn't that point 1? Plus the partial derivative of the pressure with respect to the volume. Oh, careful. Negative 8.31 TV to the negative 2. That is negative 8.31 T V to the negative 1. All right. Times the rate of change of the volume. How fast is the volume changing with respect to time? That is, it's a given. It's 0.2. All right. Okay, the rest of the problem is cleaning up negative exponents and, oh, that's a negative 2 here, right? That's a negative 2. Cleaning up negative exponents and substitute values where they correspond. So the total change of the pressure with respect time, going in the middle of the calculation through contributions of temperature plus contributions of volume, that is 8.31 over V times 0.1 minus 8.31 T over V squared times 0.2. Okay, so all we're going to do is substitute our given values for the temperature and volume. Okay, volume, substitute the rest of the problem, calculator. All right, that's all it is. So that is 8.31 times 0.1 over V, which is 100, minus 8.31 times T, which is the temperature, that is 300, divided by the volume square, that is 100 squared. And well, of course, you can verify this result using your calculator. That should give us approximately negative 0.04155. That's what I got using my calculator, all these decimals. 0.04. Oh, the units are units of pressure, which are kilopascals in this case, per second. All right. Notice the result. Notice the result because so that the change in the pressure is negative. That is, we're losing pressure. Why are we losing pressure? Well, that's because of the increase in the volume. So we're increasing the volume, and also, how do we know the volume is increasing? Because its rate of change with respect time is positive. So increasing the volume, you have more space for the particles to travel within the balloon or whatever the container it's containing the gas, and therefore there will be a lower pressure. And in fact, well, since we're looking at the rate of change, well, that's why we get a negative result. All right, unless we were decreasing the volume, well, that of course is going to make a different change. It's going to make the pressure to increase and have the total change of the pressure to increase. All right, so that was the chain rule with one variable. What if we have the chain rule for a function where we have two independent variables? Well, so what if we have, for instance, a function f, a function f or z, that depends on the first two intermediate variables that are x and y. And furthermore, each intermediate variable depends not just on one single variable t like we did before, but now they depend on two variables. All right? So in this case, well, that's not just going to be an ordinary derivative, so that's going to be partial derivatives, because now we will have the dependent variable to change with respect not just t, but with respect s and with respect t. Well, to have a better understanding of these two expressions for these chain rules, again, a tree diagram is going to help us. So number one, so from here, from these givens, we're always going to be given something like this, in terms of polynomial, exponential, whatever, every kind of function, logarithmic, I don't know. That's going to be the map, if you will. So that is z. Z depends on x and y, right? So there is a branch for x and a branch for y, all right? And at the same time, notice how x and y depend not just on t, but also on s, depend on two variables. So this is going to have two branches each, s and t. S and t. So that explains why all derivative factors and terms this time are all partial derivatives. So in this case, x is changing now with respect to variables, not just one single variable like before. That's why we had ordinary derivatives. In this case, that's why we have partial derivatives. All right. So to obtain this expression, we need to consider all the different ways all the possible ways to go from z to s and from z to t. Okay, so I'm going to use different colors for this. Let me box this with with yellow. To go from z to s. So to go from z to s, I have to go from z to x, and then from x to z. That is the partial derivative of z with respect x, and then the partial derivative with respect s, right? What about the second term? That means we have to go from s to y, and then from y to s, from z to y, and then from y to s. All right? Now let's have a look at the other partial derivative of the other chain rule expression. Well, so we're gonna go this time. So to go from z to t, let's consider all the branches that take us from the dependent variable z all the way to t. And there's two possibilities here, right? So that is from z to x and from x to t. That explains the first term right here. Partial of z with respect x times partial of x with respect t. And lastly, we consider z with respect y and y with respect t, which explains this last term. All right? Are we limited as to how many branches and variables we may have? No, of course not. For instance, let me make something up. What if we have some function w that depends on r, s, and t? All right? At the same time, each r, s, and t, each of the three depend on x, y, z. X, y, z. Oh, another one. X, Y, Z. Okay? And at the same time, why not? X and Y depend on U and V, 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 U and V. Alright? U and V, U and V, and lastly another U and V. Alright? Do we want to stop here? No, let's have more variables. Why not? How about each alpha and beta? Why not? Alpha and beta, you can add more if you want, right? So again, there's no limit. So now for instance, what if we wanted to use the chain rule to find an expression to see the change of the dependent variable w with respect alpha? You would have to consider all the different paths to go from w to alpha. That is here, 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 and then here, here. Oh, still here, here, here. Did you see how many terms are we going to have? The more variables we have, the more intermediate variables we have. Yep. So now let's a little bit of terminology. This is the dependent variable. Dependent variable. All these variables you see in the middle, well, the very last variables right here are the independent. Independent variables, or variable, well in this case it's variables. And every letter you see in the middle are called intermediate variables. For this big branch, the dependent is W, the independent variables are alpha and beta, and all the variables in between r, s, t, x, y, z, u, and v are the intermediate variables. All right, intermediate. That'll be r, s, t, x, y, z, u, and v. All of those are the intermediate variables. And guys, well, so when working with these three diagrams, because well, there's one exercise on the take-home quiz for today. So do it nice and neat. Don't do something like, oh yes, like this, and then so but budget your space so I can easily follow your work. So when I say on the quiz, write it neatly, so organized, so we can see the branches. So maybe use a ruler to budget your spaces accordingly. So actually, you can also follow the path to come up with an expression for a chain rule. Okay. All right. Let's see. Should we do an example?